Let me just point out a few things. So all of that is in the lecture notes you can look at. There's a couple really neat things that if you have a branching of a axon like this, and we have diameter 1, diameter 2, and diameter 3. So if an axon branches out, it turns out the voltage will stay the same along these dendrites as long as this as the ratio of these axons of these diameters follow a particular rule, and the branching rule is called the 3/2 rule. So, and that is, darn it, why don't I write these equations down? Diameter 1. Let's see. Well, I have, diameter 1 to the 3/2 has to equal to the diameter 2 to the 3/2 plus diameter 3 to the 3/2. If this ratio is smaller than this rule, it turns out the voltage will, if the axons are smaller, let's say the voltage is moving this way, if the axon's smaller, the voltage is going to go up and when it hits this branch. If the axons are larger than the 3/2 rule, the voltage is going to drop when it goes across that. And if it stays at that, so the branching is going to change. Another thing is that neurons, that if you let's say we put something, a sheath across this. So we're going to insulate that axon. What is that going to do to the resistance across the membrane? It's going to increase the resistance across the membrane. And what is it going to do along the axial? It's not going to affect the axial resistance at all, right? And so that's going to change this resistance, and that's going to make the length constant much longer. So it means that the voltage is going to travel much longer before it starts to drop off, right? So it turns out it also makes it faster, to propagate faster. And so this is what neurons do. This is what the glia cells do, is they put a covering on this, and then you get passive, very fast passive that goes in between, and then you pack lots and lots of channels in between, and then when this neuron, when this part here fires, it jumps over very quickly to this next section. And so this is called myelination, which increases propagation, velocity. And then you get action potentials being regenerated at these spots. These spots are called nodes of Ranvier. And they're packed with voltage-gated sodium channels, and this jumping here, jumping in French is salté, and so this is called saltatory conduction, or Latin is probably to jump. So it jumps from one node of Ranvier to the next. And so when you want to get a message down someplace fast, you use a myelinated neuron because it gets there much faster. It takes much less energy to get there. And if you lose in this myelination, well, suddenly this can't get from this node of Ranvier over to this node of Ranvier. The voltage drops below threshold before it gets here, and you get failure of conduction. And that's what happens in a lot of the demyelination diseases that happen, like multiple sclerosis and things like that. One last thing I want to show is if you think, so we can add, in these equations here, we had leak, sodium, potassium, leak. We can also add in things like the current coming in from along the axis, right? So we can, these equations here, we can write a discrete form of these equations. So we can look at, this is called I cable. We can talk about I electrode. So current coming in directly from the electrode, and current coming in from a synapse. And we are going to explicitly add these things into the next homeworks. So we're going to add in a cable, electrodes, and synapses. I forget the exact order. The cable, the current coming in the cable is going to be the voltage. We can just think of this as a series of, here's our axon, that these are chambers that are connected through resistors, right? And we're going to have a resistance, axial resistance, or leak, sorry, RL, and we're going to think this is the voltage at some K minus 1. This is going to be called a chamber at some point in space along the axis, voltage at some point K, and voltage at K plus 1. And we can look at the voltage of K plus 1 minus voltage of K divided by the change in X squared. So this is the difference. That's the current coming in from the left side minus VK minus 1 minus VK over delta X squared. And so we can just look at the voltage to the left and right. I think I may have screwed up something in that equation, because I think these guys are supposed to add, not cancel. I think, yeah, we just add these together. So we look at the difference in the voltage across between the left and right, and then we look at the difference between those two currents, right? We add them together. If all the current coming in this side is going out that side, the total charge change here is 0, right? But if voltage is coming in from both sides, the change is... So we can actually just add that directly to this equation along there in cable, and now we essentially connect a whole bunch of different models together and make the cable go, and you'll see things propagate down.